we present NeuTex, neural texture mapping for volumetric neural rendering, a method that recovers 2D view-dependent textures and 3D volumetric geometries from images. NeuTex is based on neural radiance fields, or NeRF, which enables high-quality novel view synthesis from images, but is hard to support appearance editing. This limitation motivated us to develop NeuTex to allow easy appearance editing. Let's start from a review of NeRF. NeRF represents the scene as a volume where each point in the scene has a volumetric density or opacity and a view-dependent radiance. The volume is encoded by a neural network that takes position and direction as input and outputs the opacity and radiance. Each camera pixel is then computed by the ray marching algorithm by accumulating the opacity and radiance along the camera ray. This differentiable process allows optimizing for the network parameters from images. However, we know that NeRF entangles both geometry and appearances in a volume-encoding neural network. It makes it hard to edit object appearances. To address this issue, we aim to disentangle the 3D geometry and 2D appearances. Instead of predicting an opacity and a radiance for each point and direction, NeuTex predicts an opacity and a 2D UV coordinate for each 3D points. The radiance is then predicted by a texture network conditioned on the view direction. We hope that for each point on the object surface, it will be mapped to a unique position on the UV space. For non-surface points, their UV coordinates do not matter as the opacity will converge to 0. The UV network essentially learns the UV unwrapping process, and the texture network learns the view-dependent gradient texture. In practice, to avoid discontinuities in texture space, we use spherical UV maps by predicting 3D UV coordinates and then normalize. Now, we notice that this new model has a prominent issue. That is, it often leads to a distorted UV space. We visualize this by swapping the spherical texture with the checkerboard cube map shown here. We see larger regions on the object surface are collapsed to small regions on the spherical texture, as shown in the right picture. To ensure distant points on the object surface do not map to small 2D regions, we introduce an inverse UV network. This network learns to wrap the 2D UV surface back onto the 3D object surface. When distant 3D surface points map to the same 2D point, the inverse network can only map to a single 3D point, resulting in a large cycle loss. This encourages different 3D surface points to map to different UV coordinates. To properly train the forward and inverse UV networks, we need a way to distinguish between surface points and non-surface points. Fortunately, this information is already available in the ray marching process. The blend weight for each point reflects how likely this point is near the surface. Now, we can supervise the UV networks with a cycle loss on the 3D points before and after applying the cycle map. The loss is weighted by the ray marching blend weight. Our experiments show this cycle loss can help recover a uniform and meaningful UV space. Now, let's take a look at the full architecture. Starting from NeRF, we split the network into appearance and geometry. The appearance part consists of a UV network and texture network. They construct 2D radiance textures. The geometry part uses density network to predict the opacity. NeuTex is supervised with the rendering loss and a cycle loss with the help of the inverse UV network. After training NeuTex, the texture network has stored all the appearance information in 2D space. We can combine it with other 2D textures. Here, for example, we multiply the intensity of the texture network outputs with the color of another new texture. Here, we show some view synthesis and appearance editing results on detailed asset objects and our own objects captured by smartphone. Here is a comparison of NeuTex and other methods to synthesize a held-out novel view. NeuTex gives high-quality results close to NeRF. NeuTex can also be combined with other volumetric neural rendering methods, for example, neural reflectance fields, which is a reflectance capturing technique. When the only light source is a point light collocated with the camera, neural reflectance field modifies NeRF to output volumetric density, normal, and material BRDF in 3D. Combining NeuTex with neural reflectance fields, we can extract UV space BRDF properties such as material albedo. These extracted textures are no longer view-dependent and can be edited easily. For example, color editing is as simple as drawing on the albedo texture directly. To summarize, we have introduced NeuTex, a volumetric neural rendering technique that separates 3D geometry and 2D texture to enable texture editing. It can be applied in many ray marching-based pipelines such as view synthesis and reflectance capture.